Hello, everyone, and welcome back to our series on energy modeling applications with Honeybee. And in the previous video, we actually simulated this multi-zone energy model that we built, and we loaded some of the results to color the rooms with this data, with the heating data that you see here, as well as the cooling data. In this video, we're going to take what we've learned in the previous video and start to use that to perform some thermal comfort analyses on this model and evaluate how well it is in terms of the thermal comfort it provides to the occupants. So in order to do this, I first need to actually make sure that I'm requesting outputs related to thermal comfort when I run the simulation here. So the first thing that I'm going to do is that I'm going to go over to my HP Energy tab, and I'm going to grab some energy simulation parameters. And you'll see that these provide a bunch of different ways of customizing how the energy simulation is run. They're meant to be plugged actually into this component that is running the energy simulation for us. And you'll see that one of the things that we can customize using the HP simulation parameter are these outputs, basically the outputs that we want to get from the energy simulation. So using this, I'm going to actually grab another component called HB simulation output. I'm going to drag and drop this onto my canvas here. And you'll see that this gives us a simulation output that we can then plug into our simulation parameters, just like what you see here. And let's see, and now I could actually start to decide what particular outputs I want to get from our simulation. One of these things you'll see is exactly what I've been looking for, right? These comfort metrics. So I'm going to bring up a Boolean toggle on my canvas here. I'm just going to double click, start typing Boolean and grab this Boolean toggle. And I'm going to double click the false to set it to true. And I'll connect this up to comfort metrics. So this will essentially allow me to request metrics related to thermal comfort out of my energy simulation. Now, I rather like having these outputs of cooling and heating. These are pretty useful, so I'm going to also still request those. I'm going to connect up this Boolean toggle up to zone energy use. And, maybe I'll just also connect it to this HVAC energy use. It seems useful. But all these other ones, I'll leave them as they are for now. Maybe we'll get to them later at some point if we want to understand what types of outputs they are. But importantly now, I have a bunch of simulation parameters that are actually going to request outputs that I want related to thermal comfort. And if I connect up this simulation parameter to this HB model to OSM component, you should see it's going to rerun the simulation, but this time it'll make sure to record all this extra data that we're interested in here. So I'm going to fast forward because it's probably going to take a few seconds for the simulation to finish. Okay, so that was pretty quick. And you'll see that we're still going to get our results for cooling and heating coming in through our read room energy result component. And that's because we requested the zone energy use. That's exactly what's coming through here. But importantly, now we should also be able to get comfort metrics. And while there aren't any particular outputs related to the thermal comfort on this read room energy result, we do have a component that lives right next to this read room energy result that is called read room comfort result. And if I drag and drop this onto my canvas here, you'll see that this will allow us to bring in things like operative temperature, air temperature, radiant temperature, and relative humidity. Essentially the conditions inside of these rooms of this model. So we can then use these various conditions to evaluate people's thermal comfort. So let's see, let me try and connect an SQL file up to this component. And you'll see it'll take a couple of seconds to run, but it will then bring in something that should be pretty familiar at this point. So let me connect up a panel here so you can see. So we're going to get 7 data collections for operative temperature. And we'll see that this is in Celsius and there are 760 values. So we can imagine this is essentially a data collection giving us the temperature in each one of these spaces throughout the course of the year. And I can connect these up to my hourly plot just like I did with the heating and cooling. So let's see, if I were to do that, I'm going to right click on this hourly plot so that I can turn the preview on and see this again in the Rhino scene. Let's see, I'll go over to top view. And we can see that the temperature in these spaces goes through quite some lows and highs. So let's see, in the darkest part of the winter at nighttime, it seems like it can get down to 19 Celsius or so. But when we've got the sun blasting through the windows or it's particularly hot outside, you'll see that we're getting all the way up to 26, almost 27 Celsius in some of these cases. But you'll also notice that not all rooms are created equal. Some are getting really pretty hot, whereas others aren't getting nearly as high. Some are only getting up to, let's say, 25.5 Celsius. Yeah, especially this room looks a lot more comfortable, we can see, than the others. It has much less extremes in temperature. So again, just like what we did with heating and cooling, instead of just plotting this all on an hourly plot like this, it's very useful to connect this up to the HB color rooms component. So I'm going to turn the preview back off on this LB hourly plot, and I'm going to connect up this operative temperature to the data of our HB color rooms. And let's see, and we'll go back over to perspective here. And we can see, well, right now we're just getting the average zone operative temperature when we do this. But let me try looping through a simulation step here. I guess maybe I shouldn't have gotten rid of that slider. So if I get a slider that goes from 0 to 23 again, so I'll just do that by double clicking the canvas and typing 0 less than 23. And I'll hit enter to create this slider. And let's see, and I'll plug this back into the simulation step. And we'll be able to, at this point, go through the temperature at each and every hour of the simulation. And we can see some interesting behaviors start to happen. So one thing is that we see that this room has a much higher temperature than all of the other rooms, and that's probably the result of the sun streaming through the windows at that hour. And yeah, we can see it evolve and change even more over the course of the day until, I mean, and it's interesting, we almost see a reversal. So at night, this center room is one of the warmest rooms compared to all the others. And that kind of makes sense. The outdoors are cold. It has the least amount of surface area exposed to the outdoors. And so therefore it loses heat more slowly. But if we were to go into the middle of the day, or even just to, let's say like 4 p.m. like this, right? This is one of the coldest rooms in the entire house. And it's probably for the same reason, right? It's just a lot more stable in its temperature than these other rooms that are around it. And maybe it's even useful. So we can actually look at a specific hour of the year. If I were to go over to Ladybug and bring up this component that's simply called LB calculate HOI, or HOI standing for hour of the year. And I can plug in my slider here that is the hour to the hour input of this component. And then I can plug in another slider to the month input here that goes from 1 to 12. So I'll just type 1 less than 12 and hit enter. And let's see, if I connect this up to the month, and then I'll connect up this HOI that I get here to my simulation step, you'll see that we can now actually scroll through. Let's see if I change this to June. So this is the temperature of these different rooms at 4 p.m. on June 21st. And I can scroll through the hours and see how the summer conditions are different than those winter ones. And let's see, maybe we could even see, I guess maybe this isn't the hottest day of the year. What if we were to go to something like, oh yeah, look at things get really interesting in July and in August. Yeah, I think the temperatures are getting really high up there at the end of the day. So you can really start to understand the thermodynamics of what's happening in the house by scrolling through the hours of the simulation like this. So all right, so we've only been looking at operative temperature here. And operative temperature, it's really more of a feels like temperature. You'll see that we also have things like the air temperature here, and those can be slightly different than the operative temperature. In fact, maybe it's helpful to just say the operative temperature is essentially the average between these two other temperatures we get out of here. It's an average between air temperature and rad temperature, or which stands for radiant temperature. And whereas air temperature is pretty straightforward, you can imagine it's just that temperature of the air that's within the room. Radiant temperature is a little bit harder to understand, but an easy way that you can think about it is that it's essentially the temperature of all of these surfaces that surround a person. So you can imagine if you have the sun beating down on this room here that has a lot of southern exposure, or this room in the west here, which I'm sure gets a lot of sun at 4 p.m. on August 21st, this sun is going to beat down onto the floor, and it's going to warm up that floor surface till it becomes actually warmer than the air around it and warmer than the other surfaces around it. And so that really warm floor surface is going to affect your comfort just like the temperature of the air does. So that's why I was looking mostly at operative temperature here, because it's a pretty good litmus test for what exactly the temperature that you're going to experience in that space is. But there's actually even one thing that we could do even better than just looking at temperatures like this, and that is to actually look at a thermal comfort model. So I'm going to take a break from Grasshopper for a second and tell you guys a story. And this is the story of probably what is the most famous thermal comfort model that we use today. And some of you may have heard of it before. It's called predicted mean vote. But essentially, the story of predicted mean vote goes back all the way to the 60s, where there was this scientist in Denmark named Fanger. Fanger was his last name. And Fanger was just starting to experiment with these brand new climate chambers that could really allow you to control the conditions in a space to a high degree that was never really possible up until the 60s. So he can control things like the air temperature in the room. He could control the temperature of individual surfaces around the person. He could control the airspeed that they felt, and he can control the humidity to a very high degree. And so Fanger had this climate chamber, and he had another very important resource, which was a lot of students. And so he decided with these students in his climate chamber that he would conduct some thermal comfort experiments. And he stuck his students in this chamber for an hour at a time, measuring all the conditions around the person very precisely, and trying to get also a very precise measurement of the person's clothing and of their activity level as they sat in this box. And after sitting in this box for an hour or so, doing a certain activity, wearing a certain amount of clothing, sitting in certain conditions, he would give them a survey. And basically the survey would say, like, what are you feeling? Are you feeling too hot? Are you feeling too cold? How hot? How cold? And he did this basically hundreds and hundreds of times, building up quite a large data set across all of his students, until finally he tried to take this data and see if he could try and make a model that would predict the survey results of his students based on the conditions within the climate chamber. So he picked out 6 criteria that he measured in his climate chamber studies to see if he could find at least what the average student of his would say when they were put in the climate chamber. And so he had the air temperature that he measured very well. He had the humidity that he measured very well. He had that radiant temperature that I mentioned, which is essentially the temperature of the surface around the person. He had the air speed that the person experienced, and he had the clothing and the metabolic rate, which is essentially just a measure of the activity level of the person, which you can imagine is pretty important for people's thermal comfort, because if I'm just sitting at my desk, doing some work, I'm going to have a very different temperature that I want to be at when compared to, let's say, working out in a gym. I'm definitely going to want conditions to be much cooler if I'm working out in the gym. So, all right, so taking his data set and taking these 6 inputs, he tried to construct a model using a principle that you guys are probably already familiar with if you've watched our previous video series. And that principle is the first law of thermodynamics. So essentially, what he noticed here is that the way that our buildings keep stable temperatures is that the energy going into our building has to equal the energy that eventually leaves the building in order for that temperature to remain stable. And when it comes to our buildings, right, those energy inputs are things like lights and equipment and heat from occupants in the space, as well as the heating system itself. And we lose the heat by means of conduction through the envelope and infiltration of outdoor air, right? That you can basically make an equality between those two terms as long as the temperature is stable in the space. And certainly our core body temperatures as humans need to be stable for us to stay alive. So what this means is essentially that the metabolic rate of a person, basically that heat that is generated by the body, has to equal, or at least over a long period of time, has to equal the heat leaving the body. Otherwise, our core body temperature is going to change, and we're going to be in a very bad position. we might die if our core body temperature changes too much. So you can imagine, right, if this equality is kind of violated, right, if I have too much heat that is generated by the body that can leave, I'm going to start to get hot. And so my body will start to use mechanisms to try and cool itself down and get rid of this heat. And as you guys might imagine, a really important one of those mechanisms is sweating. So I'm going to start sweating when the equation is tipped to this side. Versus, let's say if I have too much heat leaving the body than can be generated, my body will also kick into gear to try and keep this equality. It's going to start shivering essentially so that my metabolic rate rises enough to keep this heat generated by the body equal to the heat leaving the body. So, all right, so you have an intuitive sense of how this fundamental law of thermodynamics actually relates to humans. The sort of revolutionary thing that Fanger did was that he took this equation from fundamental physics and he related it to his data set that he had collected from his climate chamber studies. And using those two together, he was able to build a pretty good model of exactly what the mean vote of his students would be. Basically, if we looked at a scale here and if we looked at how the comfort survey he gave to his students was structured, he would ask them, do you feel neutral? Do you feel slightly warm, or too hot? And similarly, he asked them, do you feel slightly cool, or too cold? And he tried to essentially use his model to predict where along this 7-point scale the average student would fall given these inputs. And so he named his model predicted mean vote after the metric that it was made to produce here. And he tried to relate it also to what he called the percentage of people dissatisfied. And very simply, that just means the percentage of people who are not reporting a completely neutral, not hot, not too cold answer for his survey. And we can actually see he has a kind of bell curve that represents this percentage of people dissatisfied. And what he actually finds is that even when there are neutral conditions, that is, that on average, the typical person, the typical student you put in his climate chamber would have said that they don't feel hot or they don't feel too cold. Even when he has that perfectly neutral condition, there's still about 5% or so of students that are going to say, oh, I'm feeling slightly cool or oh, I'm feeling slightly warm. So there's actually a really important lesson we can kind of learn from this, which is if you really don't allow people to change their clothing or adapt their activity level to the space that they're in, you're never really going to get everybody happy in the space, but you can get pretty close, at least in what Fanger was finding. And generally speaking, we now have standards these days that are built around this model. Some of you may be familiar with a very popular standard called ASHRAE 55. There's a European and more international version of the standard called EN1, I forget the exact string of numbers, but it's essentially the same type of standard. Using the predicted mean vote model, we try to aim for conditions in our buildings that are 10% people dissatisfied, which you can see if I were to go back here, basically relates to a predicted mean vote between slightly cool and slightly warm. Or it's around if we're going to imagine cold as -3, -2, -1, and then 0, and this is +1, +2, +3. It's a predicted mean vote of -0.5 and +0.5. As long as we're staying in between there, we should be able to get percentage of people dissatisfied below 10%. So, all right. So we finally have at least some sort of criteria that we can use to evaluate thermal comfort in our space. And so all that I'm going to do before I wrap up this video is that I want to actually plug in these conditions that we have here into this predicted mean vote thermal comfort model. So if we go back over to our Ladybug tab, and if I were to go to this Analyze Data tab, you'll see that there's a component called LB PMV Comfort. And so this is meant to take exactly what we were looking at in the previous story that I just told you, right? So it actually has 6 inputs for air temperature, radiant temperature, or mean radiant temperature, or MRT as we say. We have relative humidity, airspeed, metabolic rate, and clothing. And using all of these inputs together, we can get a value essentially of predicted mean vote for these set of conditions. So I'm going to take my air temperature and I'll plug that into air temp. I'm going to take my rad temp and and I'm going to plug that into MRT. And maybe I'll just move this so you guys can clearly see what I'm doing. And then lastly, you'll see that we have relative humidity out of the simulation here, which I didn't preview, but just trust me that it's good enough to go into this model, this relative humidity data collection for each room. And then lastly, airspeed. Honestly, we probably are not going to have that very high airspeeds on the indoors unless there are ceiling fans or something like that. So I'm just going to leave this at the default, which is a low typical indoor airspeed. And metabolic rate can be pretty important. So maybe I'll plug something in for this, or maybe I will get a slider that allows us to adjust this. So if I grab a slider that goes from, let's say, 1.0 up to 1.3, you'll see that I chose these values based on essentially the description that you'll see for the input here. So the units of this are essentially a metric that Fanger came up with called MET, where 1 MET is the metabolic rate of a seated human being at rest doing nothing, maybe essentially but reading a newspaper. And then a metabolic rate of, let's say, 1.2 is for a standing person or maybe someone sitting at a desk typing. I mean, honestly, me teaching this video, it's probably pretty close to 1.2. So why don't I actually plug something close to that? I'll plug in 1.2 to this component here. And let's see. And then clothing might also be something that we want to adjust. So generally it looks like 0.5 is shorts and a t-shirt, whereas 1 clo is meant to be a 3-piece suit. I mean, yeah, it's talk about the 60s. Like, so this is another unit that Fanger came up with, the clo, where 1 clo is a 3-piece suit. And if there's any proof of at least the sexism of the 60s, that the 3-piece suit was the gold standard of our comfort models. But in any case, we should definitely change this because I'd imagine, especially in a single family home, people are not going to be wearing 3-piece suits around everywhere. So I'll bring up a slider that goes from 0.5, which is shorts and a t-shirt, up to 1.0. And maybe we'll say something like, 0.7. That's probably just a normal t-shirt and jeans, something like what I'm wearing right now as I teach you this video. That should be good enough for our purposes here. And so lastly, there's like one more parameter we need to plug in here, which is a Boolean input for run. So if I double click the canvas, I'll bring up a Boolean toggle, and I'll connect this up to the run input here, and I'll double click to set this to true. And it's probably going to take a few seconds because it's actually computing comfort at every single hour of the simulation for each of these 7 rooms. So you can imagine that's a lot of energy balance calculations that are run for those 8760 times 7 data points. But it's not all that long, it's still pretty good. And you'll see out of this, we're going to actually get data collections of predicted mean vote. So let's go ahead and actually try and understand what's going on here. It's been enough times that I've used this LB hourly plot. Why don't I turn the preview on this? And let's see. And I'm going to plug in a base point of maybe 50.00. And so that will at least move this out of the way so it's not on top of our geometry here. And let's see. And I'm going to plug in the PMV output here to this hourly plot. And we can see that conditions are generally close to neutral. We see that 7-point scale essentially that I showed you a few minutes ago, right? We have hot, warm, slightly warm, neutral, all the way down to cool. But we can probably see that we're definitely getting outside of the comfort range. I can see in these nighttime hours here, we're definitely getting out of the range in this case. And probably some of these daytime hours here, we're getting out of the range. The easy way that I can check this is actually by looking at the percentage of people dissatisfied coming out of this component. And if I were to plug this into here, yeah, oh, wow, we can see there's some pretty uncomfortable hours here. We're getting up to like 28% of people dissatisfied. So we're definitely not meeting a standard like ASHRAE 55 all the time in this space. And yeah, and we can see, sometimes it looked like it's because it's too cold. I bet these nighttime hours are because it's too cold. And these daytime hours, like what we see here, that must be that it's too hot, I'm sure, when we're in the summer like this and in the afternoon. So, all right, so we can already begin to see that the comfort is not perfect for our model here, and that there are probably a number of things that we can do to improve it. But I know this video has kind of gone on long enough right now. I'm going to call it pause for here, and in the next video, we're really going to start to understand why this thermal comfort is the way that it is, and maybe delve a little more deeply into adjusting some of these thermal comfort inputs to get a better understanding of the actual occupant's thermal comfort in the space. So thanks again, and I'll see you in the next video.